So I'm going to be giving, my lecture is going to be an introduction to polyhedral products. It'll be very elementary, I hope. And I'm not going to make many assumptions. I'll use some words like vibrations, perhaps, if I get far enough. If there's anything you don't quite understand or would like me to give some information about, please stop, and I'll be happy to do that. I took advantage of the gap before the intro to put some elementary constructions from homotopy theory that I will be using. I'm sure many of you are familiar with them, but I thought I would stick that on the blackboard. And the one that will rear its ugly head more than anything else is the join, which is the last one I wrote there. That will appear in the course of the lecture. So toric topology, polyhedral products has its origins in toric topology, which, by the way, is the reason the first book up there is called Toric Topology. That's your reference. That has everything I say and infinitely more is in that book. And I recommend that to anybody who develops an interest in the subject. It started with toric varieties, and people were very interested in what smooth toric varieties looked like. And an important construction within this field that appeared in symplectic geometry was something called the moment-angle complex, which I will talk about. So all these things were being done in a language that might be foreign to topologists. And then those two guys, Davis and Januszkiewicz, came along and basically did many of the constructions in a language that's more familiar to topologists. And that's what I will use for my introduction of the talk. One of the challenges of the subject is to spell Januszkiewicz correctly. I wrote it up there to avoid screwing it up, okay? Okay. So the beginning, again, following Davis Januszkiewicz, is the notion of a convex polytope. And this is the convex hull of n points in some Euclidean space. I'll put Rn. These points will be called the vertices. So for example, or maybe I'll actually put it over here. There is our simplest convex polytope, the square. And I'll try to draw another one. Tetrahedron. Those aren't too bad. My drawing skills are not very good, but that's the best I can do. So there are some examples of convex polytopes. The dimension of the polytope is the ambient dimension. This is two-dimensional. These are three-dimensional gadgets. In the codimension one faces play a special role in this. So the codimension one faces are called the facets. So in this situation, here are the facets. The planes here and the bottom triangle are the facets. The triangles and the square at the bottom are the facets. And the number of facets is a number that is traditionally labeled with M. So I'm going to let M, script F, is the collection of facets, codimension one faces. And unless otherwise mentioned, that number M will always denote the number of facets. Now, within the world of convex polytopes, there are some that are special. A polytope is simple if every codimension K face is uniquely the intersection of k facets, which I, for the moment, I'll write. So the face would equal some facet all the way down to a kth facet. So in this example, these are the facets, these edges, they're codimension 1. The vertex, which is codimension 2, is indeed uniquely the intersection of two facets. My God, I have a simple polytope. The same is true of this one. The reason I drew that one on is because it is not simple. We should have an example of an unsimple. This vertex, for example, is the intersection of two facets. So there exist non-simple polytopes. Everything we're going to talk about involves simple polytopes. Okay. So what do we do with these? What did Davis and Januszkiewicz do with these? Well, the first thing we're going to do is give the Davis and Januszkiewicz's construction of this moment angle complex associated to a simple polytope. That's the first step in this. So this is the Davis-Januszkiewicz construction of the moment angle complex over a simple polytope P, which remember comes equipped with all these facets, etc. So what they do is they take the m-dimensional torus. It is a lecture on toral topology, and there is the torus. And I multiply that by the polytope. Nothing very special yet. But then we put in an equivalence relation. And the equivalence relation is going to make heavy use of the simplicity of the polytope. So I have to tell you when G1, an element in the torus, comma, a point in the polytope, is equivalent to G2, comma, a point in the polytope. The first condition, we can't even start, the 2 points have to be the same. Now, given that the 2 points are the same, and I'll use P for the common value, that P lies in the interior of a unique face, or I guess if P is a vertex, it's not in the interior of a face, but otherwise, let's just think it's in the interior of a face. And because of simplicity, the face that contains that point P is an intersection, a unique intersection of T facets. So this would be a codimension T face, for example. That's where the simplicity shows up. Well, let's look at this torus. I'm going to write the torus. Now these are circles. That subscript is not the usual thing you see adorning the name for a circle, but each of these circles is associated to a coordinate. There are m coordinates, and I'm indexing the circles by the facets. That's what the subscript means. Well, here's a whole bunch of subscripts which came about because of my point P. So that tells me how to look for a subtorus. I could look at the circle I could look at the subgroup defined by the circles, indexed by the vertices that define the facet that contains P. And the rest of the equivalence relation is, so intuitively, I'm multiplying my complex, my polytope, by product of tori, and over some faces, I'm collapsing some circles to a point, and those circles that I'm collapsing to a point are indexed by the facets that define the face I'm over. That's all that's going on. Let's do an example. Whoops, I want to do it on this blackboard. Let's take the polytope, which is the interval. It's about as much as I could do. They get out of control, and without certain mind-altering drugs, it's hard to draw the pictures and whatnot. So I'll only use the straight line for my examples. Two facets, the vertex 1 and the vertex 2 are the two facets, codimension 1. So what do? I take S1 indexed by 1 cross S1 indexed by 2 and multiply that by the interval. And I'm going to write the interval now, the way you should think of this, and this is actually useful for the next step, which I'm going to slur over, I should think of this part of the interval as in some sense a neighborhood of this vertex. And this interval is really just a neighborhood of this vertex. That's the way you should think of it. Excuse me?
You mean 2?
1. Oh, I see what you know what? Make this, I see what you mean. Does that work better? Thank you, thank you. Okay, so what do? I'm going to group this. Don't forget, when the torus is over this vertex, I'm going to collapse this to a point. So let's gather that together. I'm going to take so I just regroup that bit. So I guess this is an example of the transitive law. And what is happening? At this origin, this point, this circle is getting collapsed to a point. So this is turning into a cone, which I'll rewrite as D2. It's the cone on the circle. And this is near 1. This circle is getting collapsed to a point, thus turning into the cone on the circle. But the disk crossed the circle, union the circle crossed the disk, and the union is over 1/2. That is exactly, where is it? The definition of the join. And the join of a circle with a circle, I'll just say it, I mentioned it up there, is the 3-sphere. It's the suspension of the smash product. So in this particular case, if I go to Davison-Januszkiewicz's construction for the simple polytope P, I end up with a manifold. It happens to be a 3-sphere. In general, we end up with a manifold of dimension m plus n. M was the number of facets, if you recall, and n is the dimension of the polytope. So it's a good way of getting manifolds which are equipped with TM actions, torus geometry. Okay. Well, we need another construction. We want to generalize this. So this is, oops. We want to generalize this. And to generalize this, I have to remind you about some notions from the ideas of simplicial complexes. simplicial complexes. So this is a definition of an important object in topology. We often denote the simplicial complex by K, and there's a set. I'm using the same letter M for reasons that will be clear as I proceed, which are the numbers from 1 to M. And K is a subset. It's a collection of subsets of the numbers from 1 to M and has a very simple property. If sigma belongs to K, and the subsets that belong to K we call simplices, and if tau is a subset of sigma, then tau must belong to K. That's all it is. That's a simplicial complex. And given a polytope, what we are going to do is associate to it a simplicial complex. But before I begin, I should give the most important example of a simplicial complex. Suppose K equals 2 to the M. 3 points. Every subset belongs to the simplicial complex, and we typically draw it like this. Here's the points 1, 2, 3. The vertices 1, 2, and 3 belong. The edges are denoted by the subset 1, 2, and the full simplex would be 1, 2, 3. This is called this is a 2-simplex. In general, this would be an M-1 simplex. And what I have here is a picture for the simplicial complex. Here's some abstract nonsense about sets and subsets, but one often can draw pictures for these things, and this is called the geometric realization. We write it that way. Another example would be the set 0, 1, 2, 0, 1. I mean, that's just the set, but the picture would be 0, 1, and 2, and 0 on that edge. This would be the geometric realization of that simplicial complex. One can give a precise definition, but I'm not going to do that. So what is the use of that? Well, given a simple polytope, we are going to start with a simple polytope P and construct a simplicial complex Kp. And what that's going to be is that associated to a codimension K-1, a codimension K face, which remember, because of simplicity, I can simply write it this way. I'm going to associate that to a K-1 simplex. I might have the numbers backwards, but we'll see. So for example, did I write that down right? I was kidding. It's a P, it's actually a, oh, I think I might have the numbers right, actually. So let's do an example. The polytope, which is the square, has faces F1, facets rather, F1, F2, F3, F4, vertices V1, V2, V3, V4. Associated to each facet, that's a codimension K face. I guess I associate that to a vertex. Am I getting the numbers? I think I need an n minus k or something. I always get that backwards. But the picture tells you what you should do. Associated to the facet, I take a vertex, so I'm still labeled by the facet. There's the facet F1. This is the facet F2. This is the facet F3. And this will be the facet F4. There's an edge, a one simplex in this simplicial complex, which would correspond to an intersection, a codimension 2 face. In this case, the vertices are the codimension 2 faces. So V1 is the intersection of F1 and F4. So the simplicial complex includes that edge. V4 is F1 and F2. So I'm going to label this edge by V1. That is not typical. You normally label the vertices with V's, but for the sake of this drawing, I'm not doing that. And this is the vertex V3 and the vertex V4. The interior is not part of the simplicial complex, okay? That would be K of the square, all right? So it was observed, I think it goes ideas of Strickland, Buchstaber, and Panov, that associated to the simplicial complex constructed from the polytope, I could give an alternative definition of the moment angle complex, which sits inside an M-fold product of disks, a huge cube, which I'm going to do now. So given the simplicial complex K, and when I write contained in M, I simply mean that this is the vertex set. K is a set of subsets of the vertex set 1 through M. And I'm going to define a space D sigma. It is indexed by the simplices that are in K. In this example, the simplices are the vertices and the edges that I drew down here. And what it is a product of spaces yi. The yi's will be either a disk, a D2, or a circle. Nothing mysterious about it. And what I do is if the subscript is in the simplex, I take a copy of the disk. And by the way, when I write the simplex here, I also mean, I use that symbol for the points in the simplex, the numbers in the simplex. So I don't want to have to put bars around it when I want to distinguish the simplex from being a vertex in the simplex. So I is one of the vertices of the simplex. And I take the copy of the circle if it is not a vertex in the simplex. It's as simple as that. Now remember the condition on a simplicial complex. If I had a simplex and a subset of that simplex tau, then that tau must be a simplex in its own right. So that means that I have this diagram induced by all the simplices that are in K. And the only simplicial complex I've given you examples of yet so far come about from duals of polytopes, or the simplicial complex associated to a polytope. But I could take the union over all simplices of these D sigmas, where the union is induced by the obvious inclusions from the circle into the disk. This turns out to be homotopy equivalent, is it equal on the nose? Or, well, I don't know. Homotopy equivalent to the moment angle complex of the original polytope P. Remember, the moment angle complex of the original polytope P was this guy that Davis and Januszkiewicz constructed for us. This is an alternative construction for that. And I think it's good to give an example here. Well, the example I gave before, the polytope was the edge. So the dual simplex, shall I ask? What is K of a line? If my polytope is a line with two little vertices sticking out, what is K of that? There are only two facets, the two vertices, and the picture looks very much like the picture for the line. It is 2 points, 2 disjoint points would be the K. So here it is. K of the edge is a point 0 and 1. Thanks for Tony for making me put the indices right. And what do I do? What is this construction? Over 0, over the vertex 0, I put a D2, and I'll put a subscript to denote which vertex that D2 is sitting over. And the other vertex, the 1, is not in the simplex. So I multiply that by S1. That's the contribution for D sigma when sigma 0. And then I take the union of that with what goes on at 1. And this product is over the circle, across the circle. That should look familiar. I think that looks very much like what I wrote down for the interval. But the whole thing generalizes, and that's true in general. But something nice is true. This construction does not really care that I started with this simplicial complex associated to a polytope. I could do this for any simplicial complex. Nor does this construction really give a damn that I'm using D2 and S1. I could use any pair of spaces. So this construction gives insight into a generalization, which is called a polyhedral product. So I'm going to give that definition now. Maybe I should save it. So this is the polyhedral product. And the data that it starts with, we have a simplicial complex K. I don't give a damn where it came from. It's on the street out in the front, came into the building. It doesn't have to have started with a polytope. All it is that abstract definition of a certain collection of subsets. And again, this notation simply means the vertex set for K are the numbers 1 through M. And then I need a collection of spaces, pairs of spaces, and I'm going to make them based. So these are based pairs of spaces. This is cofibrant. AI is contained in Xi. And to be able to simplify it and avoid using homotopy colimits, I will assume everything's a CW pairs. That's all I understand anyway. And I have one of these pairs for each of the vertices. And for shorthand, we write this X bar, A bar. In our definition over here, all the X's were D2, all the A's were S1s. But with this general data, and it's been generalized beyond that, I could still define D sigma. And I do exactly what I did over there. It's a product of spaces yi, colon, yi equals xi if I belongs to sigma, ai if I does not belong to sigma. And guess what? The polyhedral product, now I'm going to use this notation for the moment, is the union over all sigma of d sigma, and given that it's CW pairs, I don't have to worry about some technical issues about taking limits and so on. This is a notation that is used as an alternate notation. I'm sorry about my Blackboard organization, but it is sometimes written as x bar, a bar, superscript k. In Buchstaber and Panov's book, this is the notation they use, and since I sent you there as a reference, I will use this, but most of my life, I have used that. Excuse me? I will give that in a second. Good, all right, let me do that. Tony mentions that I should give you another notation. If we happen to have started with a polytope, and x bar, a bar is D2 S1 for all I, so we are getting the MAC. Well, rather than write MAC all the time, this is denoted, I can't do a bold Z, but Z sub P. That would be the notation for the MAC. Okay. I just want to mention a few properties which I will not verify. Well, let me discuss the naturality. The naturality. So I've written it. It looks a hell of a lot like a functor where it depends on these three entries. If it's a functor, I have to be careful and specify how it behaves with respect to morphisms. So let me specify that, naturality. One is more or less obvious. If I have a function which is a function of pairs, namely each xi maps to an xi prime, such that ai, which is contained in here, gets mapped to ai prime. So I have a map of pairs, then I don't think it's rocket science to see there's a very natural map, same K, there's a map induced. One can also show if I have two maps which are homotopic as maps of pairs. So I have maps of pairs and restricted to X, they're homotopic, and restricted to A, they're homotopic. Then I guess I should give a name to this. I'll call it Z of F. I have a little memory of the Z notation. Then Z of F1 is homotopic to Z of F2. So homotopy maps between the pairs induce homotopic maps on the polyhedral products. More interesting, perhaps, is the functors, how it behaves with respect to maps on the simplicial complex. So I'm going to leave this up here. We're going to need this here. And this idea goes to Strickland. So suppose I have a map. Actually, I should try to get my notation correct so I don't screw that up. I have a simplicial complex on a vertex set N mapping to a simplicial complex on a vertex set M. That simply means it takes simplices to simplices. It does not say that it's one-to-one on the vertices. It does not say it's surjective on the vertices. It simply says that it is one-to-one. I mean that it takes a simplex to a simplex. And for the general construction, we have to assume that the xi's are monoids. In other words, all I'm saying is that there's a map, a product that, so I can take two copies of xi and map it over to one, which restricts to a map on the pair. That's the assumption, and given that, we'll tell you how things map over. So I'm going to find a map from the product of all the xi's to the product of all the and x1 to xm is simply going to be sent to numbers y1. I think I have the order wrong. N to m to ym, and yi equals, and what's the natural thing to do? Remember I said this map, I guess I didn't give a name for the map, call it F. It's not necessarily one-to-one. There might be a number of vertices here, which there might be a vertex here that comes from a whole bunch of vertices over here. So what you do simply is you multiply, let's see, am I going the right way? So all you do is you look at a subscript here and look at all the vertices that map to that same vertex. So given a subscript here, there's a whole sense of vertices here that will map to that subscript. So the xi's are going to be mapped over to many xi's. There are different copies. And you use the multiplication to multiply them all together to end up in one copy of an x. And you send it to 1, which is the base point. I forgot to mention the base point. If is is not in the image of F. So maybe I confused that too much, but it's really a very simple idea, and I'm just going to repeat it. Given any vertex here, there might be 3 vertices here that map to that. So where do I send the x? I have x1, x2, and x3 all multiplying going to the same vertex. I multiply them together, give me a point over that vertex, and that's where I send it. So that's what that does. And we note D2S1 satisfies the multiplication property. So for the MAC, we could define maps between simplicial complexes. And I'll also note if F is 1-to-1, so I never have multiple points, I don't have to multiply. So I don't have to induce that condition. So one way or another, let me simply say there is a functorial property at the level of the simplicial complex. So it's a nice functor. And what is it good for? Well, we're going to find that out in the course of this lecture. I'm going to give some examples. An example. Get rid of this. So the example I'm going to use, I'm going to get Ln, or maybe, you call it Ln, n distinct points. As a simplicial, I should call it Lm, I guess. As a simplicial complex, it sits in M, but the only vertices is sigma equal to 1 point. There's no edges, just a set of distinct points. And x comma a, I'll take to be the interval comma s naught, the interval and 2 endpoints. So the question is, what does that thing look like? I claim that the polyhedral product, I'll use I upper Ln, Lm, is something interesting. Start to draw a picture of why it's interesting. Whoops, where'd I draw it? Ah, here it is. I'm going to explain what we get from this for m equal to 3. Now remember, the polyhedral product, this is a good review of what the polyhedral product is. It is equal to, then we're going to have m equals to 3. There are three coordinates. So remember, I have the only vertices are the only simplices are the vertices. So over the vertex 1, I have the interval, and the remaining vertices, I get the subset S naught, and so on. What is this? So here's where colors come in. Well, first of all, the vertices, there are 8 vertices. S naught has 2 points, etc. There are 8 points here. Think of these as like binary expansions. Forget about the interval for the moment. So I wrote out the vertices here. 0, 0, 0 would be one of the points. Thinking of S naught cross S naught cross S naught. And so on. 1, 0, 0 would be one of the points. What would I draw for the green stuff? This would be when in the first coordinate, I have 3 coordinates. In the first coordinate, they differ in the first coordinate. The 0 is attached to the 1. Think of S0 as a 0 and a 1. The 0 is attached to the 1. So this set, they differ on the first coordinate, will give me these edges. See if I could do this right. In this coordinate, the blue, they differ in the second coordinate. See if I could draw that right. This one differs here. This one differs here. This one differs in that coordinate. And this one differs in that coordinate. And the last one, there's an edge if they differ in the third coordinate. What do I do? That's going to actually be red. Differing in the last coordinate. Differing in the last coordinate. Actually, this would look better, I guess, if I... yeah, that looks a little better. you get a hypercube. You get a graph which is the n-dimensional hypercube. In general, for an arbitrary m, I get an m-dimensional hypercube. So we're getting a nice geometric object out of the polyhedral product. Yes, sir. Excuse me?
Isn't it the one skeleton? One skeleton.
That's the, well, it is the graph. It's the one skeleton is the whole complex. There's nothing else in the simplicial complex, nothing else in the polyhedral product.
It's not the whole cube.
Well, it's called the n-dimensional hypercube if we just mean the one skeleton, as you said. I'm sorry, I'm just not used to the terminology. But yes, it's the one skeleton of the cube. Okay. So I'd like to give another example. Let's see if I could get this. Suppose K is the boundary of an n-gon. So K is the bound. That's a very poorly drawn n-gon. I'll be the first to admit that. And what do we get if we take the same pair, but for this K? It turns out by a theorem of Coxeter, well, it's easy to see one always gets a surface. But this is a surface of genus, and let me try writing it out correctly. One gets a surface of that genus, and it's a good inductive exercise on the definition of the polyhedral product to see if you could reproduce that. It's not that bad. So if I take the n-gon, I get a surface. If I take disjoint points, I get the one skeleton of an n-cube, thank you. But we have a natural map. Namely, I can include the disjoint points into the vertices of the n-gon. So if I take the polyhedral product let me call this K sub n for the m-gon. By just including the vertices, I get an embedding of the let me not have to say the one skeleton all the time, but he's completely right. I get an embedding of that into a surface of that genus, S sub That's not at all obvious that you could do those embedding, and in fact, they are the best possible. Using an Euler characteristic, one can show you can never get it into a surface of a smaller genus. But I wanted to do that to illustrate how the naturality in the polyhedral product sometimes gives non-trivial geometric information. So, excuse me? Well, if you do a squared, n has to be at least 3. So I did draw, I have the picture. For n equal to 3, I believe I get a two-sphere. 1, 1, 1 plus 1. And indeed, I can embed that thing in the surface. And I think it's pretty obvious I can't do better because there's nothing smaller than the two-sphere. But you can play around with that for different numbers. And I really do think it would be fun for you to try to prove Coxeter's theorem. I have to admit, I had to write it out, but I'm not going to do it in this lecture. So the next thing I want to do, let's see, some fibrations. We've got 15 minutes, so I think I can introduce some fibrations. Oh, by the way, are there any questions before I go on to the next topic? And the fibrations, actually the ones I'm going to use are quite general. So to start, I'll assume I simply have G a group. And what group do you think we're going to be interested in? The M torus. This is the underlying group that's controlling everything. There's something called E of G, which is contractible. Chalk keeps on breaking. And has a free G action. For example, if G is the circle, EG can be taken to be the infinite dimensional sphere, which has a natural action coming about by thinking of the circle as the units in the complex numbers, and S infinity is contractible. There is a, given a topological space, in this case a CW complex, I could take EG and map it down to the quotient. That's given the name BG. Not that we'll use it in this lecture, but it is called the classifying space. And the fiber is a copy of G. This thing's contractible. So again, I'm making some assumptions about what you might know about by fibrations. If these are foreign words to you, just don't worry about it. If I have a contractible fiber, that means that this space is the loops of that space. So one of the reasons for introducing BG, it is what's called a de-looping of the group. But that's not going to play a role in this lecture. But what will be useful, again, is our example. BG is CP infinity. If you believe DG was S infinity, then it's not a big leap to believe BG is CP infinity. Okay. The next thing we have to know is how I can glue a G space. Oh, yeah. Okay, these are some words, and given my handwriting, you can't read them anyway. But suppose I've got a space X with G acts. That G acts. What I want to do is take X and replace the G with the copy of X in a uniform way. And the way we do that, the way this can be done, I'll work in the general situation. So I can take EG cross, let me make that a smaller cross X. I have the group acting diagonally. That's a terrible small x. I have the group acting diagonally on this. And by the way, notice the group acts freely on this product, no matter whether X is bad or not, because it acts freely on the EG part. And I can mod out by the action of the group, and it's written that way. This is EG cross X modulo of the G action. It still maps down to BG, but all I've done in each fiber is taken G crossed over G with X. This is what I've done to the total space, but in each fiber I've got that. But this, of course, is just X. So I've succeeded in gluing X fiber-wise in a uniform way. So let us go to our example. Our group is the M torus. And I'll remind you that BG for this group is the product of CP infinity, because these things behave very nice on products. And my space X will be the polyhedral product model we gave. Sorry, I introduced that notation. I actually introduced Z sub P for a polyhedron, but Z sub K simply means the MAC, the polyhedral product D2S1 for K. This has a TM action. This is a TM space. So there exists a vibration There exists such a vibration which is fundamental in this object. This has a name. This is called the Davis-Januszkiewicz space. Its cohomology is completely understood, and it's an invariant of the underlying K. It's called the Stanley-Reisner ring, but I'm not giving lectures on the cohomology, so I could avoid that. So with the time remaining, I'd like to exploit this vibration with an example. Let's see. Now, I will have to be a little quick here because I'm running out of time, but I'd like to exploit that vibration. With the notion of something called partial quotients. What do I mean by that? Let's see if I know what I mean by that. Well, we have our group Tm. Suppose I find a subgroup of Tm which will be equivalent to some R sphere. Suppose one thing I forgot to mention, very important. If X is a free G space, then this is called the Borel construction. I should have used his name. Then EG crossed over G with X is of the homotopy type of X mod G. So this is a way of freeing up an arbitrary action of a group of a G space, sort of getting a free version of it. Might call it the homotopy quotient space. But this is an important fact. Suppose I have such a thing, and H, suppose we have the following assumptions. H acts freely on the moment angle complex, ZK. Now, given that H is a subgroup of Tm, I could write Tm as H plus the quotient Tm mod H. And I'm going to call this G. This G is not the previous general G. I just don't want to have to write Tm mod G all the time. So suppose I have G acts freely on ZK. And G is equivalent to a Tm minus R, that R. So why is that good? If I have time, I will give examples of such things. Some things called quasi-toric manifolds come about in this construction. I'm just going to give the construction and then probably end with two examples that make it easy and make it interesting. Okay, what good is this? Well, I could look at zk mod h. Don't forget, h act freely on zk. I could take a look at zk mod h. I've used up some of the TM action. This still has the leftover action, the coordinates that I did not use. This has a Tm minus R action. I mean, Tm decomposes in that way, and I've used up H by quotienting it out. There's still this much left over. So I get a fibration, just as we did with the moment angle complex. Yes, use zk mod H. I'm going to have the Borel construction. This is not mysterious. We've seen this already. And let me just give a heuristic for why we think we have seen this. If I take the Davis-Januszkiewicz space, which recall is ETM crossed over Tm with zk, well, don't forget Tm decomposes, and all this is very natural. So I'm going to take E EG crossed over G with E, what do I call it, H, crossed over H with ZK. I just decomposed Tm. It's a direct sum. There's this natural decomposition. But H is acting freely on ZK, so I can replace this with that. So the Davis-Januszkiewicz space, the thing I know and love, which fit into a fibration which I unfortunately erased, is exactly this guy over here. Why is that good? ZK mod H, this fiber, okay, let me say it over here. I'm running out of time, so I'm rushing, and I'm going to end the example without any reasons why this example is true. Examples, there exist H's such that we get the following fibrations. CP2 connected sum CP2 with the opposite complex structure. Remember, the whole point of this was that I always get DJ at the bottom. I'll write DJ to a product of CP infinities. There are actually two, but I don't care. Choosing a different H, I can get S2 so if I had time, I'd show you the H's that produced either a connected sum of complex projective spaces or S2 cross S2. But the homotopy groups of CP infinity, I did not mention that. The homotopy groups of CP infinity is about as easy as it can get. The stuff in dimension 2 and nothing else. So that means these two spaces have isomorphic homotopy for I bigger than 2. These two spaces have isomorphic homotopy for I bigger than 2. But these two guys are the same. So we conclude that the higher homotopy groups of this space are exactly the same as the higher homotopy groups of this space. That is not obvious. And in fact, there's a lot more one can say. This is just it's not even the tip of the iceberg. This is like shaving a little bit of snow off of the iceberg. But there's a whole story here about giving us isomorphisms of homotopy groups, which are not at all obvious. And just make a point for those of you who's ever tried using the atom spectral sequence to compute homotopy, especially unstable homotopy. The technical term is connected sums are a bitch. These are very hard. Whereas this, no one knows the homotopy groups of the two-sphere, but rationally we do. So the rational homotopy of that is exactly the same as the rational homotopy of that above 2. That's an amusing thing to know. In any event, I've run a little bit over. I apologize, and thank you.